Hi everyone, today I'm going to talk about the history of zero. There are four stages that we want to be able to discuss, each one representing a growing complexity all the way from early cognition to the construction of the sweeping societal constructs of mathematics today. And God said, "Let there be light." I won't try to offer any real exegesis on this topic, but there is a parallel to the way that creation begins from something out of nothing, and the way beginning of cognition is recognizing something out of nothing. Much like the biblical creation story, what we recognize is the thing in the void rather than the void, or that which shaped our concept of nothing. Before cognition, we can react to stimuli. We can recognize a light and fulfill whatever biological impulse is prompted. This nothing is best described as a state of rest in the brain, in the absence of stimuli, but isn't quite a concept. Cognition develops as we develop a sense of self and can differentiate the light as external. Eventually, we can distinguish between two lights as individual things. Essentially, to develop a concept of nothing, we had to remember that there was a light after it fades. This allows us to establish a sense of precedence and past, making meaning out of the Genesis story's account of coming from nothing. Eventually, we move on to the categorical. As number sense and individuation develop, the idea of nothing developed closer to a number as a placeholder. Some form of tally marks are probably one of the oldest systems of recording numbers, where there's a one-to-one representation of whatever is counted, or accumulation. Eventually, someone had the idea to use the diagonal slash to group sets like we do now with groups of 5. Systems like these are what eventually evolved into systems more like Roman numerals, where different symbols could be used to represent limited groups that count up to a number. Anyone who's tried to use Roman numerals to represent large numbers knows that the limited set of groups makes this difficult. It also doesn't lend itself very easily to algorithmic operations like we are used to in decimal place in our decimal system. As you can imagine, the next step would be a placeholder system. There were several systems that evolved, mostly separately. We're actually going to go back in time a bit first to the Babylonians. Babylonians took the concept of grouping and created placeholders around 400 BC. They would group together by joining the wedges in the clay tablets that they used to keep records. They used two symbols for tens and ones in a cumulative way, but kept place values by powers of 60. Place values obviously necessitate a zero, as in the lower example, in case you're counting 3 or more powers with no value in between. This is not the same as the number 0, since it would not have been used alone and had yet no properties as such. Additionally, using the same wedge mark for placeholders as single ones became fraught. In many tablets, it's difficult to tell the double wedge mark from ones, and seems to lead to copying errors as well. Although China started using the place value systems earlier with counting rods, the first system had no way of denoting a blank space between groups. It was a little confusing. If you look at the second example, they would have groups of 3 and 2, but there's no real, for example, you might not be able to tell if there were 2 rows of 0 between or just 1. The system they would later develop was to use boards to group the counting rods. While they still didn't develop a symbol, using the boards created an obvious space between place values that was much more convenient. The boards held place values in powers of 10 from right to left, where each row was a number. They were used for addition and subtraction vertically, the same way we use modern decimal notation. In this example, this is the numbers 315 and 203 ready for an operation. Around the beginning of the Christian era, the Mayans developed the shell symbol as a placeholder for 0. As a refresher, their place value system was vertical, so that the columns represent individual numbers, while rows represent powers of 20 within individual numbers. This has also facilitated horizontal algorithmic operations, which brings it much closer to having the properties with which we are familiar with, as it now acts as the additive identity, or has the property that when added to any number, the number remains unchanged. However, because it still has no numerical value itself and would not have been used alone, it isn't quite there. It's in India in the 7th century in 628 Common Era that we see the first use of a symbol with the numerical value of 0 that we are familiar with today. In Brahmagupta's book written completely in verse, he officially graduates 0 to a number by providing rules to compute with 0. For instance, he writes, when 0 is added to a number or subtracted from a number, the number remains unchanged, and a number multiplied by 0 becomes 0. In this inscription from Gwalior in central India in 876 CE, you can see the number 270 used in the Indo-Arabic numeral system that we use today. As you already know, our system uses 10 different symbols to represent the numeric values 0 through 9 in a decimal or base 10 system, which was pretty nifty in the wake of the more primitive systems we just saw. The word given to 0 in Sanskrit was sunya, or empty. Europeans took quite a while to start using 0 as this number. 0 was translated literally as the empty in Arabic in the 9th century, or as al-sifru. It finally arrived in Europe around 1200 CE when Fibonacci brought Indo-Arabic numerals and the decimal system. Here, al-sifr was translated in Latin as cifra and sephirum, but was controversial. For those who use 0, cifra became a code word. The legacy of the secrecy is still in our English word cipher. After 0's gradual acceptance, the first generation of children to learn about it was in the latter half of the 16th century, a generation that happened to produce William Shakespeare. Shakespeare begins to use not only the idea of nothing, but plays with 0 as a number that he can manipulate with defined rules, perfectly primed for metaphor. Polixenes in The Winter's Tale plays with the idea that 0, this thing that can have no value, can multiply any single number into thousands using the decimal system. And therefore, like a cipher, yet standing in rich place, I multiply with 1, we thank you, many thousands more that go before it. In the famous Demands of Lear, Shakespeare plays with the idea that multiplying by 0 results in 0, as nothing will come of nothing. And finally, Shakespeare plays with the actual symbol for 0, this O without a figure, newly popularized but already carrying the weight that we associate today, or rather lack of weight. The numerical value of 0 actually plays a neurological role behind its social rise. We can follow the development of conceptualization in children through adulthood. The hesitancy in Europe to accept 0 may reflect the development of the concept in children. Infants have been shown to react to puppet shows showing mathematical operations, where they react more confused to incorrect operations like 1 plus 1 equals 1, but confusion is not shown when 0 is involved, which researchers assume comes from their inability to conceptualize a null value. Children 3 to 4 can begin to call the idea of nothing reached by counting down to 0, but usually use 0 in operations. By around 6, children can start to use 0 as an actual value. As we've seen before, people's number sense works in groups of 2. Higher reasoning animals such as monkeys, some parrots, and dolphins can be taught to respond not just to stimulus but also a lack of stimulus, reaching the sensory category. Monkeys can be trained to associate 0 with empty categories, but can't reason out what reward to expect when shown 0, indicating they can reach categorical reasoning, but not numeric. Essentially, you can train them in an experiment to expect a certain number of treats if they're shown a number, but when you show them 0, they just act confused because they don't understand what no treats mean if they're going to get treats, setting up this sort of expectation dichotomy. The interesting and comparable fact is that monkeys reason in sets, just like humans, doing operations by sets of 2 and then combining the values of those sets before any further reasoning. While children generally all reach a level of implicit understanding of 0, adults have various levels of development in their explicit articulation of 0 as a value. As with animals, our number sense is based on set comparisons, but empty sets, or 0, are difficult for our brains. The expectation of something but receiving no stimulus is called stimulus absence response. This response seems to be triggered by the brain entering into some sort of expectation state in which it can decide what that the expectation was not met, and then trigger its own stimulus on the lack of that expectation, a sort of representation of zero. Having built this concept of zero, we can apply additional layers of abstraction. These cumulative layers create the more complicated number theory that we're familiar with today. Let's look at some of those properties of zero. This first statement, while clear, represents a process that took the majority of human history to derive, while all the rest have been derived relatively recently. Zero's sign could equally be seen as much as an inherent property as an abstracted rule which coincidentally includes it. What really makes a positive or even integer? We've defined it as greater or less than zero, which seems to work out all right. The parity of zero, or whether it is even or odd, might really be said to be abstract. Intuitively know that even means that it could be grouped evenly into two groups, and zero seems to defy any sort of grouping. Yet no groups of two are just as divisible by two as any other, which is the definition of even, so we add this property. Finally, we get to a property that separates zero from the other numbers that no consistent rule can overcome. Division by zero is impossible, not only because breaking something up until it becomes nothing causes its own problems, but we can produce easy examples that are obviously observed, like showing 1 equals 2 if we multiply 0 by 1, set that equal to 2 times 0, and then divide both sides by 0 so that it leaves 1 equals 2. Now, that's not quite how our brains work. Since our brains conceptualize numbers as sets, I think it's helpful to observe some set theory to understand what the disparities between a concept of zero and nothing might be. Importantly, an empty set is not the number zero. It has no value that could be added to the value 1, for example. But simultaneously, it's not quite nothing, because an empty set is still just a set. So, the original name of zero as empty reflected some truth about the way we conceptualize the world. We can develop amazing systems of rules and properties that can be used, like Euler's number, deemed the most beautiful equation for incorporating all five of the most essential numbers, e, I, pi, 1, and 0. But 0 remains an abstraction. So, I cannot decide whether I think 0 was invented or discovered. And I think this is primarily because of my second question. Is 0 an essential quantity that is separate from nothing that we've discovered a limited way to describe? Or is 0 actually just a concept that we can manipulate in a system of concepts that is related to nothing? I lean towards invented, as we can see it developed as a way to be as a symbol that could be manipulated. Yet the concept of nothing certainly seems to have some substance, more